Albert Einstein and quantum mechanics are two of the most famous names in the history of physics, and their relationship is as fascinating as it is complex. Einstein helped lay the groundwork for quantum theory, but he also became one of its most vocal critics. In this video, we will explore the tension between Einstein and quantum mechanics, the debates that shaped modern physics, and the lasting impact of their ideas. Einstein's contributions to quantum physics began early in his career. In 1905, he proposed the quantum theory of light, suggesting that light is made up of discrete packets of energy called photons. This idea explained the photoelectric effect, where light hitting certain metals causes electrons to be emitted. The photoelectric effect could not be explained by classical wave theory alone, and Einstein's work earned him the Nobel Prize in Physics in 1921. Despite this, Einstein grew uneasy with the emerging theory of quantum mechanics in the 1920s and 1930s. The new quantum mechanics, developed by scientists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, introduced principles such as superposition, uncertainty, and probabilistic outcomes. Instead of deterministic predictions, quantum mechanics could only provide probabilities for measurement results. Einstein famously rejected the idea that nature is fundamentally probabilistic. He is often quoted as saying, "God does not play dice with the universe." He believed that quantum mechanics was incomplete, and that there must be underlying hidden variables or deterministic laws that could fully describe reality. For Einstein, the randomness of quantum mechanics was a philosophical problem, not a physical one. One of the most famous debates between Einstein and quantum mechanics occurred through his correspondence and discussions with Niels Bohr. Bohr defended the Copenhagen interpretation, which accepts quantum indeterminacy as fundamental. Einstein proposed thought experiments to challenge the theory, including versions of the EPR paradox in 1935, named after Einstein, Podolsky, and Rosen. The EPR paradox highlighted a problem Einstein saw with quantum mechanics: entanglement. According to quantum theory, two particles can become entangled so that measuring one immediately affects the state of the other, no matter the distance separating them. Einstein called this spooky action at a distance and argued that it implied quantum mechanics was incomplete because it seemed to allow instantaneous effects, violating locality. Bohr responded by defending entanglement and the probabilistic nature of quantum mechanics. He argued that the theory correctly predicts experimental outcomes, and that entanglement does not transmit usable information faster than light. This debate became a philosophical and scientific cornerstone, exploring the nature of reality, measurement, and the limits of knowledge. Einstein's skepticism did not stop the development of quantum mechanics. Experiments in the late 20th century, particularly Bell's theorem tests, showed that entanglement is real and that no local hidden variable theory can fully explain the correlations observed in quantum experiments. In other words, many of Einstein's objections, while philosophically motivated, were inconsistent with experimental evidence, yet Einstein's critiques were not in vain. They inspired deeper thinking about the foundations of quantum mechanics, leading to more precise experiments, the development of quantum information theory, and even technologies such as quantum cryptography and quantum teleportation. In a sense, Einstein helped drive the field forward, even while questioning its principles. Another area of tension was Einstein's belief in determinism and continuity, contrasted with the discrete, probabilistic events predicted by quantum mechanics. He could not accept that physical reality at its core could be inherently uncertain. Quantum mechanics, however, has repeatedly proven itself as the most accurate description of microscopic phenomena, from electrons and atoms to photons and molecules. In simple terms, the conflict between Einstein and quantum mechanics was about the nature of reality. Einstein sought certainty, hidden order, and deterministic laws. Quantum mechanics embraced probabilities, superpositions, and entanglement. Both perspectives have shaped modern physics. Einstein's work laid the foundation for relativity, while quantum mechanics explains the behavior of matter and energy at the smallest scales. Even today, physicists explore the boundary between relativity and quantum mechanics, seeking a unified theory that reconciles the two. Einstein's vision of a complete theory of everything remains an inspiration, while quantum mechanics continues to expand into computing, communication, and fundamental research. In the end, Einstein versus quantum mechanics was not a simple battle of right versus wrong. It was a dialogue that challenged assumptions, drove experiments, and deepened our understanding of the universe. Einstein's skepticism forced the scientific community to clarify, test, and refine quantum theory, while quantum mechanics revealed a universe stranger and more fascinating than even Einstein could have imagined. The story of Einstein and quantum mechanics teaches us that science progresses through debate, questioning, and exploration. It shows that even the greatest minds can disagree, yet both perspectives can lead to profound discoveries that transform our understanding of reality.